All right, so here we're supposed to look at the life expectancies in the US are always rising because of advances in healthcare, increased education, and other factors. Now, the rate of change measured at the end of each year, so that's kind of a key piece here. It's the end of each year of life expectancies for women in the US between 1970 and 2010 is modeled by the function f of t, where t is the number of years since 1970. No, f is measured in years, the life expectancy per year chronological. Okay, so between 1970 and 2010, when was the life expectancy for women growing least rapidly? All right, so what do we do here? Well, here we need to find the derivative, it sounds like. So least rapidly, we need the derivative. So f prime of t is equal to what? Well, we're going to bring the 2 down there, so it's going to be 0.0008 t, and then minus 0.022, okay? Now, when is it growing least rapidly? Well, when f prime of t is equal to 0. So we have to set that equal to 0 and see when that is. And so we can go over here. Let's clear that out. Oh, well, we can do that by hand here. We don't even need it. That's a linear. So basically, we're just taking 0.022 divided by 0.0008, if I put all the right zeros in here. So 27.5. All right, so that is going to be when t is growing least rapidly. Now, we probably should put this into the time frame here. And so 27.5 is going to be our value. And so what does the 27 indicate? Well, that's 27 years after 1970. So that's 1997. And then this half, that says, okay, well, that's going into the next year. It's half of 1998. And so what's half of 1998? Well, that would probably be, it's going to be the end of the month or the end of the year. So it's probably the end of the month. So it's probably going to be sometime in July of 1998. Because again, it says it's the end of the year. So I'm assuming that half would be the end of the month. So half of the year is 6 months. So half of that at the end is going to be end of it's going to be, so I would say around July of 1998. You know, you could say mid 1998 as well, but you know, I would say that would be a good option there. All right. So by how much is the life expectancy for women projected to increase between 2000 and 2010? All right. So what does that do? Well, if we remember, what we could do is one thing to recall. We usually are going to look at the sum of I equal 1 to n, and we're going to take the limit of that as n approaches infinity, so a lot of things here, of our f of xi and delta x, okay? And this is going to require a lot of tables. All right, and I'm not going to do that many tables here. So if we remember, we talked about something called the integral, and it was usually the definite integral, and we went from 0, or well, a to b. Okay, so depending on what your a and b are, is going to be your definite integral, and that was just of f of x dx. Okay, and those were equal. And so what I'm going to suggest is, instead of making an infinite number of tables to get, you know, this delta x to be really, 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 really small, I'm going to say, let's take the integral here. Now, in the book, it actually says to take all these tables and do all those tables, but we're not going to take the time to do that. We're going to do this. And so, again, this is for part B. And so what are we going to do? We're going from 2000, which is going to be what? Well, that's going to be between 30, and 2010, well, that's going to be 40. So we're going to take the definite integral between 30 and 40 of our 0.000 t squared minus 0.022 t plus 0.36. And then we're going to have our dt, and because this is in t's, we'll say dt. So now we're going to plug that into our calculator. And so let's go back to our calculator. We'll learn a new way to use integrals in our calculator here. You go to math, and then we're doing the function integral, okay? And so that's number 9. And now it looks like what we just typed in over here. You know, if we go back over here, we did, you know, the integral from 30 to 40 of our function. So let's do that. So we went from 30 to 40, And now we type in our integral. And now we have to convert it to x's, so that's okay. 0.1234. Then we had x squared. And then we have minus 0.022x plus 0.36, and then our dx, okay? And guess what? When we hit enter, boom, we get our answer, 0.8333333. So wasn't that easy? A lot easier than those tables. So again, 0.8333 and so on, okay? And so that's going to be our value. And so now what we have to kind of decide is, what is our value going to be of? Well, that's going to be in, if we go back up here, it's going to be in basically years per year. So the integral is going to be in years. And so this is years. How much is the expectancy projected to increase? It's projected to increase 0.83333 years between 2000 and 2010. All right. Now, what other information is needed to determine the projected life expectancy for women in 2010? Well, guess what? We're going to need to know the life expectancy in 1970 when it all started to get the one in 2010. Because if we don't know this one, all we know is it's getting, increased, but, to where, we don't know that. And so that's as far as we can go. So we cheated here. We didn't do a lot of tables. Instead, we did the definite integral, which gave us the same answer. If we would have done all those tables, as you go through each one, you're gonna, if you go up to, I don't know, 20, and then you do 40, and then you do, whatever, however high you go, each one is going to get us closer and closer to this value of 0.8333, and it kept repeating after that. Okay, so we just kind of moved ahead a little bit quicker than we were supposed to, and we did this with the definite integral. All right, so let's do another one before we pause here. So we're going to do blood pressure. So it says the blood pressure varies for individuals throughout the course of a day, typically being lowest at night and highest from late morning to early afternoon. So the estimated range of change in diastolic blood pressure for a patient with untreated hypertension is shown in the table below. And we're supposed to model the data. Then we're supposed to solve for the times at which the output of the model is 0, and of what significance are these times in the context of blood pressure, and use a limit of sums to estimate the change in diastolic blood pressure from 8 a.m. to 8 p.m., and then write the definite integral notation for this result. And finally, why is it not possible to find this patient's blood pressure at 8 a.m.? All right, so we're going to go to our calculator. And I don't think I remembered to put this in earlier. Yeah, so I don't have it in, so I'm going to pause, and I'll be back after it's typed in. All right, so I've got it typed in, but a key thing we need to remember is what are we going to do? So since we have these times going from 8 a.m. all the way through the PMs back to the AMs again, what we're going to have to do is we're going to have to base this on since 8 a.m. And that's everything's based on from 8 a.m. to that time. So what we're going to do is we're going to say, well, that's 0, then 2, 4, 6, 8, and then we won't be able to probably write 10 barely, and then 12, 14, 16, 18, 20, 22. Okay, so we'll put those in for our tables. So let's do that, and I'll show you what I've done. So again, I just went and did all that, and then if you keep going down, it'll show down to the 22. So what's our graph look like? Well, to me, that looks like a pretty good parabola. So let's try that to start with. So quadratic would be number 5, L1, L2, vars, and then we'll go into 1. And so that's going to be what I consider my equation here. So let's write that down. 0.03, let's go to 3 decimal places, x squared, then negative 0.718, and then 3.067. And okay, so it's pretty good. So let's look at our graph to see if it really does fit. Yeah, that looks pretty good. Let's go with that. All right. So we said that for a model for the data, well, that was going to be, let's call it P for pressure. Let's call it X so we don't mess up the variables. 0.030x squared minus 0.718x, and then plus 3.067, and it's millimeters of mercury per hour. All right, so that's going to be our data, or our model. Now we're supposed to solve for the times at which the output of the model is 0. Okay, well, that's going to be, and this is the rate of change. We didn't say that, but it's the rate of change in the blood pressure. Okay, from 8 a.m. to, we said, 8 p.m. All right, so that's what we called it. All right, now let's go find those zeros now. So we need to find that 0, and we need to find that 0. So second trace number 2. Let's go ahead and go here first. So that's a positive. Let's go right. There's a negative. So our first 0 is going to be 5.586. Okay, we'll write that one down. And so then our second 0 is going to be on the other side. That's a negative, so that'll work. That's positive, so that'll work. Our guess, so we get 18.128. All right, so those, again, that's times. So what do those times mean? So let's go write them down, and then let's think about what these times mean. So our first one, for B, we had X is equal to 5.586, and the other one we had X is equal to 18.128. All right. So what does that mean? Well, we're going to be 5.586 hours after our beginning time, which was 8 a.m. So if we do that, it's going to be 8 a.m. plus the 5.586. Well, we can take 8 plus 5, and we're going to get, that's going to be 13, which is 1 o'clock if you do military time. We can keep it that way. And now we have to take 5.586. I'm not going to do that by my head. 0.586. Oops, we want to get out of here. 0.586 times our 60. Wait a minute. 0.586. Oh, I'm going to say that's not the right number there. That's the problem. I don't even know what I typed there. All right, 35 minutes. So that's going to be 1335, which is 135. Now the other one, if we add 18 to 8 o'clock, that's going to be 2,600 hours, which is, if you think about it, 2,400 hours is midnight. 2 hours past that is going to be 2 a.m. And then we had the 0.128. So 0.128 times 60. And so that's going to be, that's greater than half. So let's call that 8 minutes. So, all right, so let's go back. And so that was 13, and we said it was 13:35. Okay, so military time, or 1:35 p.m. Now, the other one, we said we're going to take 8 a.m. plus our 18.128. And so we said that was 26 something, but 26 is going to be, it's a 24-hour day. And so 24 plus 2, so it's going to be 2. So it's going to be 0.2. And we said that the 0.128 was 8 minutes. So 08. And that's going to be basically 2:08 a.m. So again, military time is really nice to be able to use here because we can, go up to the 24 hours, and then after that kind of go from there. And so, 02 is 2 a.m. Okay, oops. All right, so now we have that. So we have our times, 1:35 p.m. and 2:08 a.m. All right, so for the times which that is 0, of what significance are these times, basically our importance. And so What are those importance of times? Well, the first one is going to be the rate of change. We're going to have 2 pages here, I think, with all this stuff. The rate of change of blood pressure and crosses. Remember, it crosses on a downward slope. This is how it was doing it. So the first one is going crossing here while decreasing. So the blood pressure is a relative maximum at that point. Okay, and so that's the relative max at 1:35 p.m. So that's probably when you're the most stressed out during the day, and so that's going to be when that was. Now the other one is at 2:08 a.m. So here, the rate of change of blood pressure crosses while increasing, because now we're on the upward slope. If we look at this, we're on the upward going, we're up slope. So the blood pressure is a relative minimum. Okay. All right. So again, that goes back to, when it's changing different directions, we're going to have that. So let's see here now. Let's go back to C. Use the limit of sums to estimate the change in diastolic pressure. Write the definite integral notation for the result. Why is it not possible to find the blood pressure at 8 a.m.? All right, so let's go to the next page. All right, so we're to write the integral here. So if we do that, we're going to have going from 8 a.m. to 8 p.m. Well, 8 a.m. we said was 0, and 8 p.m., well, that's 12 hours later. So our definite integral is going to be from 0 to 12 of, now we just plug in our function we found. What was that? 0.030x squared minus 0.718x, and then plus the 3.067 dx. And guess what? We can use our calculator again to do that. So let's plug it in. Let's clear that. Let's do our math. Number 9, 0 to 12 of, then we had a 0.030x squared minus 0.718x, and then plus 3. Well, actually, you know what we could do? Did we get it in here? You know what? We can get a really exact answer here. So let's go quit that. Let's go back in here. I just thought of this since we actually have it. So let's do the, no, let's go back over here. All right, now let's put our 12 back. Since we already have that over here in this, let's just say vars y1. Then we don't actually have to type the whole thing in here. That's going to make our life a little bit easier. Plus, we'll get a little bit more precise answer. And so that gives us 2.53846. And so let's take it to our normal 3 decimal places. So that was equal to 2.538 millimeters of mercury. So that was going to be the change there. Okay. So that's the rate of change in the millimeters of mercury. Now, what does that tell us? Well, why is it not possible to find the patient's blood pressure at 8 a.m.? Well, they didn't give it to us. So for part D, okay, so we don't know what it changed to. So, where was it at? Where did it go to? We don't know. And so because of that, that causes us to not know what the answer is. And so that's why it's not possible to find it. All right, let's stop and come back with this one.